Okay, thanks a lot. So today I want to talk about this project I've been working on for a few years now called Adapton. I'll try to explain what that means later, but it doesn't really mean much. But it's about incremental computation. And the work I'm going to be talking about is joint work with my PhD student who's also here, Kyle, who's in the audience. And we're at the University of Colorado Boulder. So let me start at a super high level. What do I mean by incremental computation? That term can mean a lot of things. Really what I'm talking about is computations that get run over and over again. And the idea is, the second time I run it, at time 2, I'd like to sort of make use of the fact that I already ran it a moment ago. So ideally, if input 1 and input 2 are related by some small change that I can describe, I'd like to use some kind of general purpose change propagation mechanism to avoid rerunning the computation from scratch and get the new output faster. That's what I mean by incremental computation. And I'm going to make this claim that incremental computation is everywhere. Most of it is fairly ad hoc. There's a reason people do it, though, is because it makes things faster. So I'll just run through some quick examples. There's spreadsheets, of course, makefiles and build systems. I'm changing the code and need to recompile. IDEs kind of take this further, and they're more kind of real-time. They're giving you kind of like real-time type analysis, maybe even test results and binaries as I type keys. Databases, they call it the view maintenance problem in databases. Web browsers are incredibly incremental. They're constantly re-rendering things as the DOM changes. And then there's games and simulations where you're rerunning various kinds of physical simulations or other kinds of simulations over and over again. Some of you may have seen proof assistance, where I'm interactively trying to prove things, and I'm changing definitions and changing my proof script. And I don't want to have to sort of start from scratch every time I do that. So my big question, I guess, what drives my research is wondering what unifies all these things, all these different domains, all these different problems. So they all have some input that changes, they have some computation they conceptually repeat over and over again, and some output they want to produce fast. So really what I want to do is kind of move towards a more systematic solution, and we're not there yet, but I think the point is to sort of identify the problem and what is the general form of this problem, and what does the solution sort of look like. I claim that as a programmer, which I do a lot of programming, I'm sure you all do too, I want to think about a from-scratch algorithm, not the algorithm that takes changes directly and reasons about changes directly. So somehow from that from-scratch algorithm, I want to derive the incremental behavior by using a change propagation mechanism of general purpose. That's the goal I have in mind. So it's simple because I get to think about, as the programmer, the from-scratch algorithm, not a per-change algorithm. It's correct in the sense that if the change propagation mechanism is proven correct, then by writing the from-scratch algorithm correctly, I get the right change propagation behavior. And finally, I have a notion of efficiency because I can always compare against some super optimized, really fast from-scratch algorithm and determine how good my change propagation mechanism is. So I'm going to sort of argue that Adapton is starting to achieve these goals, and it does so through programming language design. So it's all about programming languages for me. I'm going to try to make that more clear with more examples. So here's an example from the literature. This is something that algorithms people study in academia. Incremental convex hull. So the input is a bunch of points. The output is the subset of the points that if you sort of snap a rubber band, they hit those points. And yet now you can imagine a moment later I have a new point in my point set. And I don't want to recompute the hull from scratch. I want to just like update the hull I computed a moment ago. So it turns out people study this and they use it in a lot of different domains in computer science. So it's an important problem as an algorithms problem. It's so important that someone wrote in 2002 a whole PhD dissertation about this, the 2D version of convex hull in an online setting. And if you go and read this thing, it's 100 pages of algorithms and proofs. Basically, it's implemented in LaTeX. There's no implementation other than that. And this is a figure that I liked out of it. So the idea is that the algorithm is really thinking about all the different weird corner cases that comes up. How do I reuse the computation I just did? What's sort of damaged about that computation? How do I fix it? The thing is, what I said a moment ago is I want to reason about the from-scratch algorithm. And I don't see how this picture relates to that. It doesn't directly. And I'm sure the person who wrote the dissertation could tell me that, but as a programmer, I don't really get it. Okay, so here's Adapton's approach. It's much, much simpler. I write a from-scratch algorithm like QuickHull. You can find it in a textbook. And I use language tools to instrument that algorithm. I record an execution trace. And then when changes happen later, I have this change propagation mechanism that figures out what steps were invalidated by that and tries to cleverly and quickly re-execute those steps and propagate the changes. So this is a graph that comes from some dissertation work I did in C, but I'm going to show you more graphs like this, so I want to kind of explain it in detail. This is the graph I kind of care about, so it's sort of like, how good are we doing? The x-axis is me as a human interacting with a thing, changing input and observing the output. And the y-axis is how long I've waited in total for this thing to respond to all my changes. So initially, the red line, the line that uses incremental computation, is often slower, because you have to invest in creating some cached data structures. And then at some point, because you've done that investment, you start to win, because as more and more interactions happen, you can update really, really quickly. And what's happening basically is asymptotics. Asymptotics wins all the time if things get big enough and take long enough. So the version that's green, basically, quick call is a divide by conquer algorithm, so it's n log n, and then you sort of multiply it by where you are on the x-axis, that's the cumulative time. And the version that uses incremental computation, basically you make this investment and you pay some constant c, but then the update time is logarithmic, not linear or superlinear. So you start to win after a small number of changes. That's what we want. And of course, the goal is to make the investment as small as possible, get that crossover as far over that way as possible. So asymptotic improvement, I mean, you can see basically this log factor doesn't have an n in it. It's not dependent on the total problem size, at least not linearly. Okay, so the other thing I want to say about these kind of text PhD dissertation solutions is that suppose I have a way to compute convex hull incrementally, and now I have another thing that assumes that I have a convex hull. How do I plug them together and compose? That's another bunch of dissertations. So they're not generally compositional. And by being a programming language solution, I want my change propagation algorithm to have this property of compositionality. I want to plug functions together and have that be the incremental version of that composition. Okay, so let me show you graphically what I mean by that is, if I have some input and some output and something that relates them, some computation, I want to be able to sort of realize this equivalence that if compute can be decomposed into C1 and C2, then I should be able to sort of transition between these views, when it's convenient to. And I'll come back to this later and show you an example. Here's the example. So as a proof of concept, imagine you're trying to write an IDE. And the simplest IDE I could think of was a reverse Polish calculator. You have this text buffer, say an Emacs or Vim or whatever your favorite text editor is. You're typing keys and you're moving your cursor with the mouse or keyboard or whatever. And now you want to maintain at all times what the evaluation is of this text buffer as if it's a reverse Polish calculator. So if you don't remember, basically what it does is it kind of like pushes things on a stack, and then when you get to an operation, it pops the stack and pushes things, and you get this output stack in general, not a single answer, but a bunch of answers. What's on the stack at the end. So this is the problem. We want to do reverse Polish calculator incrementally. The input is a text buffer. The answer is a stack of some kind. And PL basically says, well, we should think about decomposing this to make it simpler. So if I can separate it into some function that lexes the text buffer into a sequence of tokens, then it's easier to write an evaluator that evaluates those tokens. And then if I kind of like think a little bit more carefully, the text buffer is just a sequence. The lexer is basically folding over the sequence. The tokens are another sequence. The evaluator is another fold. So it's all just sequences and folds over sequences. So if we can do that, then we can solve this problem. Okay? And we used Adapton in Rust, which is what I'll be talking about for the rest of the talk. And this is an actual performance problem we got. So currently, we haven't really optimized the engine. I wrote this engine before Rust hit 1.0, and I didn't really know Rust very well at the time. So I think there's a lot more we can do to push down the initial investment. But I'm showing the same plot I showed you before, where with this Rust native code, it's super fast initially. But every time I change the text buffer, I have to rerun that fast code. And eventually, after some number of changes, about 12, the initial investment I made starts to pay off. And why? It's because of this asymptotic thing again. With Adapton, I can update in log time, not linear time. So the text buffer can be gigantic. In this case, it's 100 or 1 million characters. We can do 10 million characters. It doesn't matter. The picture's going to look the same. Okay, so let me tell you a little bit about how Adapton works, but still kind of at a high level. There's this thing called the demanded computation graph, which is what I mostly want to explain. This example is going to be kind of a toy example, but then I'll scale it back up to the reverse Polish calculator. So there's two kinds of things in the dependence graph. There's basically cells that can change over time. So the first two lines of code here, kind of imagine as like cleaned up Rust code where I allocate two cells, numerator and denominator, 42 and 2. And then there's this other thing called funcs, which are basically just suspended computations that can rerun incrementally. So I make a func called div, which is going to divide one by the other. I haven't run it yet, so it's just kind of floating in space there. And then I make another func that checks to see if the denominator is 0 and returns none. Otherwise, it returns sum of the division. And it references that division func I made a moment ago. So now that I've kind of done this setup, the next thing that happens is interaction. And what interaction basically is sort of inspecting the root of this thing, which is this this check func, and then setting one of the inputs or maybe both of the inputs by changing them. So imagine the first thing I do is I say get check. Then I have to run this thing from scratch. And it goes and checks the denominator. Okay, it's not 0. So now demand the division. The division gets those values out of cells. The thing to note here is that I'm recording the values that I observe on the edges, these dependence edges. So that'll be important in a moment. And I finally get the answer and return the answer, which is sum 21. And then after from scratch evaluation is over, I go and make a change. And in this simple scenario, I just maybe change the denominator to 0. And now you notice that 0 and 2, 2 on that edge there, are not the same value. That will become important in a second. And there's this dirtying algorithm that just goes and eagerly dirties all the transitive dependencies. It dirties the edges. Those are all potentially inconsistent, just the way that 2 is inconsistent with 0 for denominator. When I go and get the new, now I'm back to the mode where I want to see the new output. So I force or get the value of check. And now I have to go into this cleaning mode. I don't want to re-execute everything again, but I'm going to try to reuse things if I can and re-execute things I have to re-execute. In this case, check is observing a value that's not currently the denominator. So I have to re-execute it. So I rerun it. I delete the edges and rerun it. And I get a new value, 0. And now the condition switches to the other branch, right? So I don't do the division anymore. And I just return none. And I can do the same thing and kind of flip it back. So if I set the denominator back to 2, I dirty again. Then when I do the get check, I reforce. And I see 2 again. And now this is the interesting thing is the next thing to happen is the condition flips back and will demand that I get div. And well, I can try to clean div before I go and re-execute it. And div last saw that 2 is in denominator last time I ran it. And 2 is currently the denominator. So I get to reuse it. And I can just clean it. And in general, it's, this isn't a big win, but if that subgraph was huge, it'd be a huge win. Okay, so that's the basic idea of Adapton, is that you're creating cells and edges, and you're cleaning and dirtying as you make changes and re-execute. Okay, so the high-level idea is dirtying is eager. I eagerly dirty the transitive dependencies, but cleaning is demand-driven. I left dirty edge on div, and I didn't delete div from the dependence graph. It kind of hung around. And the other important thing is sort of, if you care about this kind of thing, mathematically on paper we have a model of this, and we've proven it's consistent. It will always give you the answer that you get from running from scratch. I'll come back to that point, I guess, later in the talk. So now let's talk about large dynamic dependence graphs, not these tiny ones. So back to this picture. I want to do the reverse Polish calculator. So I'm going to have to kind of be a little bit more abstract than I've been. A reverse Polish calculator is basically going to have 3 steps, not 2. The first step is I need to lex the characters. And rather than show you like all the ref cells in some huge tree, I'm just showing you like the kind of root ref cell with a tree picture inside, or a triangle inside. But imagine that thing is some data structure with more ref cells inside. And when I force or get root, the first thing it does is it runs that first line of code, and it makes another tree-shaped data structure, which is all the funcs that read the first tree. So there's kind of an isomorphic tree there, which I'm kind of abstracting out here. And it produces a list of tokens, a stack of tokens. And then the next thing I do is I turn that stack of tokens into a balanced tree of tokens. And I'll explain that in a moment, why I do that. And the last thing I do is I do the kind of same pattern again, as I fold over the token tree and evaluate and get a stack of answers. So why do they make these trees, or why do I care about trees? It's because dirtying and cleaning is going to traverse this graph. I want the graph to basically be a balanced tree. Otherwise, it's not efficient. So we're constantly making balanced trees, and I'll tell you how we do that later in the talk. So now I can do the same thing I did before, where instead of changing 42 to 0, or changing 2 to 0 and 0 back to 2, I can basically do edits. So we have this data structure called a random access zipper, which is kind of like a really nice representation of a sequence where you can move a cursor around randomly, insert and remove stuff, and it's all in log time. So that's how I represent the text buffer with the characters. And once I do that, I'm going to dirty some path in this dependence graph. And you notice it's just the path that goes through Lex and then this kind of root node, reverse Polish calculator node. I don't dirty the rest of the graph yet. And then when I go and I want the new answer, I have to reevaluate these 3 steps. So I go and reevaluate this step, and I get to reuse a ton of stuff because of the tree representation. But that then dirties something in the toTree call. I do that next, and that dirties something in the token tree call, and eventually kind of push the dirty stuff out and clean everything. And that all happens in log time, log in the size of the initial text buffer. Okay, so I kind of made this point that we want to avoid deep calls. If we had linked lists, all of our dependency graphs would look like big, long linked lists, and cleaning and dirtying them wouldn't be very efficient. So we want these basically trees and probabilistic trees. The other thing I'll say is that we have other representations we're working on for sets, and they have to, again, kind of reinvent new representations of sets, because things from the literature like ABL trees and so on, they don't really have the right incremental properties. They're very history dependent, so they record too much information and induce false dependencies. So a lot of the work we're doing is not just, say, like making runtime systems, but also designing new collections data structures and new algorithms for them. So I mentioned that for sequences, we use random access zippers, not lists. And for sets and maps, we're working on more efficient versions of these things called hash tries, basically a variant of a trie. Think of it as like a purely functional hash table. And we also have a paper that presents this random access zipper in a kind of non-incremental setting. So it's, I think, 120 lines of OCaml code. You could port it to your favorite functional programming language or non-functional one. So you could look that up. Let me just tell you really briefly how that works. So it's based on this idea of a negative binomial distribution. So imagine I have these elements A through F, and I can send each one to some, in a deterministic way, I can map it to an element in a negative binomial distribution. So you tend to get big numbers very, very infrequently, and little numbers very frequently. That's the idea. And then you can build a probabilistic balanced tree on top of that idea. So that's the idea in a nutshell. The cool thing is you can build this thing in linear time, just scanning through the list once. And then when I make a change, like removing A or any other thing, you can sort of prove that you can update the tree in log time. That's important for us. So these trees are also stable. They're not history independent. So given the sequence, it always maps to the same tree, which is important for us. Okay, I mentioned the investment is really high in some cases. So we're working on ways of reducing the overall investment in this cache, this dependence graph. So to give you an idea of what we're comparing here, the implementation we're working on right now is in Rust. We're basically trying to compare against what would an intelligent programmer writing idiomatic Rust code do, and try to beat that. So in Rust, you have vectors, arrays essentially. You can do maps over them, which kind of become really tight for loops. And so imagine I'm taking this huge array of numbers and converting them to strings, for instance, just something simple. So we do the same thing with our level tree, which is that tree representation I just mentioned. And the knob we have to tune is like how big the leaves of this tree are. So rather than store a single element, we can store a vector of elements. And how big that vector is impacts the overall size of the dependence graph that we make. So here's a kind of busy chart, which I'll try to explain quickly. So this line that's going up linearly, that's the native line, like the Rust code running. And we also, when we set the size of the leaf to be that size, so basically have a tree with one leaf that's a big array, lo and behold, it's exactly the same performance. The other lines correspond to making the leaves smaller. So the next line down is when the leaves are 10 elements. So there's a pretty big investment, but then it's really, really flat. And then some of the lowest best lines have fairly large leaves, like 10,000 or 100,000 elements, but they're also pretty flat. So yeah, so that's just some preliminary results, and we want to generalize this to other structures other than sequences, like sets and graphs. In summary, Adapton is a simple programming model. They just have these thunks and cells. There's a change propagation algorithm that's designed for these graphs that they induce, that we've proven is always consistent with from-scratch evaluation. And we're basically, what this, you might think of FRP, and I'm happy to talk about FRP with anyone. A lot of flavors of FRP build static graphs. And what I've shown you is basically our graphs change dynamically as the data structures that they're working over change dynamically. So that's the big difference with FRP. I've given you one example of a data structure, this random access zipper, and we're working on more. So the future sort of ongoing work is doing more of this auto-tuning stuff with collections for sets and maps and graphs. We also want to build a higher level implementation language where instead of having to write Rust code, for instance, you could write maybe Ruby code. And if you use our collections, they'll just be incremental. So something higher level. And of course, we want to write more applications. So one of the things I've been doing is talking to the Rust core team. The Rust compiler, does anyone use the Rust compiler? Yeah, okay. Has anyone tried to do -- release on it and compile something big like Rust? It takes a long time because it's not incremental right now. And they're trying to figure out how do we make this big, complicated piece of software incremental. So thankfully, they've kind of reached out to me, and I'm lending whatever expertise I can there. So that's one cool, really cool application of this stuff. And the other thing we've been thinking about is maybe that this crowd would be interested in is how to do static analysis as my program is running. So imagine I had some kind of JavaScript VM, and I just pause the world conceptually at every single step to reanalyze the entire heap. And if I can do that incrementally, then I can do it. Like, it'd have to be really fast, but that's kind of like the holy grail is essentially getting whatever static analysis you want to run at every step of the program. Anyway, so I'm happy to talk about any of that stuff, either now or offline. So thanks. I'll take questions. I know there's a break too, so probably not too many. Yeah.
So maybe a basic question: how's incremental computation different from the self-adjusting?
Yeah.
I read about.
Oh, I'm so glad you asked that. Yeah, there's a rich history here. So in the beginning, there was a bunch of different ideas, dynamic programming, like memo tables. There's a lot of dynamic programming problems that can be solved by just recording a memo table. There's these things called attribute grammars, which are really in vogue in the 70s and 80s, but basically it was like static dependency graphs. And specialized languages like for incremental collections and stuff. There was this work that my PhD advisor and his advisors worked on, self-adjusting computation. So I guess at a super high level, the main difference is these algorithmic techniques behind the scenes. They have a special way of representing the dependency graph as a total order. And then certain things aren't very efficient. So in my really toy example, I showed you kind of leaving some of the graph dirty while we executed other parts of the graph. In self-adjusting computation, it's kind of like a global, I call it the batch model. So there's one monolithic dependency graph, and you walk through it, conceptually skipping over things you can skip over and removing things that are no longer consistent with the current input. So you end up flushing things from cache maybe too easily. The other problem is because of the way they represent things, if you want to like exchange two intervals of time, they can't do that efficiently because of this representation. So they have to kind of delete one of the intervals and re-instantiate it. What we're getting with Adapton is basically this demand-driven change propagation algorithm. So it's not this batch thing we have to go through the whole world. It's based on demand. And the other thing we get is that the dependency graph is really a partial order. So you can move things around, like swap things in order, and it works out better. But to be clear, we are drawing like a lot of inspiration from self-adjusting computation. Yeah.
So would it be accurate to say that they still get the asymptotic wins, but you run a lot faster in practice because of your advances, or is that?
We have to put in some extra log factors because we're building trees and we don't have this. They have this total order thing that has all these constant time guarantees.
Oh, okay.
And we have to put in an extra log factor in some places. But it's, when you're, as an algorithms person, when you're thinking about the analysis of your algorithm, you have to consider what kind of changes can I permit efficiently. As soon as I have one of these things that needs to swap the order, then it kind of blows up in your face. And if you want to be demand driven, I keep imagining like a spreadsheet where I have different sheets, and whatever sheet is in my face, that's what I want to keep up to date. The other sheets don't need to be up to date all the time if I'm not looking at them. Yeah. Yeah.
Can you talk a little bit about the scheduling of funcs and whether it's single-threaded, multi-threaded?
Yeah, at the moment, everything is just single-threaded, and that's just for simplicity because even getting that to work required a bunch of work. But yeah, I have this vision of scaling this to multiple threads, and then there's this question of what the right programming model is, which raises all the usual questions of what the right programming model is for multi-threading. I keep imagining I want one graph per thread and then message passing between them, but I haven't really thought about it a lot. Maybe other designs would work well in some applications. That's a great question, though. I'd like to work on that problem. Yeah.
Oh, gosh, a couple of things. One is a special case of this was dealing with dependencies when we changed object definitions in the self virtual machine and invalidating, inlining selectively. We have this whole dependency structure. It's a special case of your incremental computation. So just another one for your list. But as I look at this, I'm wondering about its connection to efficient functional data structures and also, what was the other thing? Well, talk about efficient, time travel debugging. That was the other one.
Yep.
So seems somehow there are connections there. You have any thoughts you want to say about that?
Yeah, so it's funny you mentioned time traveling debugging. When I started at Maryland as a postdoc, I started working on this project because a PhD student at the time who named this thing Adapton, I can't explain why he chose that name. He was working on time traveling debugger, and he started asking me questions about my PhD work, which is on self-adjusting computation. And he was inventing new persistent data structures to support it. So I don't know a lot about that space, but that was the original inspiration of this work. And it would be nice to go back and connect it to it, but I'm maybe not the right person to ask about that, since I haven't kept up with what the latest time traveling debugger technology is. But I think one way that this kind of system can really benefit certain settings would be if you're just adding data, say you're, I don't know, a company where you just get a lot of data from the internet and store it somewhere. You're just adding stuff to a database, right? You're very rarely deleting stuff from the database. But this model is robust enough to handle that. So imagine I go and revise time. I go back and say, okay, pretend that event in the past didn't happen. Replay the rest of the history as if it didn't happen. Retroactively change the history. That's the kind of setting where I think this model could help.
And is this a good implementation technique for functional languages under the covers?
Yeah, the original implementation of this Adapton system was, well, there was a Python prototype that didn't last long and then OCaml. And we moved to Rust basically because the garbage collector is our enemy. I'd be happy to talk about that with anyone, but we would often spend or waste half of our time just having the garbage collector look through our dependence graph for garbage, and there wasn't any. So that was the original motivation to move to Rust. And it's worked out pretty well so far.
Had a lousy garbage collector.
Yeah. Yeah. Maybe if I had a better one, it'd be an awesome test of any garbage collector, how smart it is, because it basically breaks all the generational assumptions. Okay. Thanks a lot.